Well, let's look at an example of a function that I think we all know does not have an inverse. Let f, with domain all real numbers and range 0 to infinity, be defined as f of x equals x squared. So you should verify, you should convince yourselves that the domain is all real numbers and that the image or the range is this. Well, that's easy to see. The easiest way to know that the domain is all real numbers is every real number can be squared. We usually run into problems when the domain is not all real numbers because we'll have a fraction that has x in the denominator. And so x could never be 0, for example. Or you have a radical where you can't have if x is under the radical, you can't have a negative number under the radical. That's when you run into problems. All polynomials have a domain of all real numbers. Okay, so that's a great function. We all know what the graph looks like, and we can tell that it's not one-to-one. So it's not going to have an inverse. But, and why isn't it one-to-one? Well, just take the y value of 1, the height of 1 on the graph. F of negative 1 is 1, f of positive 1 is 1. Two numbers mapping to 1 means it's not one-to-one. So suppose we didn't know that. Suppose we didn't know what the graph looked like. We could say, well, I don't know if f inverse exists. Let me do the recipe and see what happens. The recipe says you have f of x equals x squared. I'm sorry, the first step is you replace f of x with y. So y equals x squared. Second step is you interchange x and y. And 3 is the only one that has to do any algebra or work at all, really, mathematics. Solve it for y. So what do we have? We have y squared equals x. All I did is switch places. So to get this by itself, I have to use what we call the square root property to get y by itself. But you have to remember to put the plus or minus on the right-hand side when you take a square root. When you have y squared and you want to get y by itself. Notice, if you forget the plus or minus, you're going to think it's a function. And you'd say, number 4, you would just say, well, f of x equals radical x. Yeah, x squared has an inverse. It's square root of x. But that's not true because, for example, this is not even a function. If two functions are inverses, of course they are both functions. This is not a function. If you plug in a 1 for x, well, what do you get? Radical 1 is 1. You get y having two different values. So it's not even a function. So that's where we find the error in the recipe. Well, let's graph. I'll use a different color. Let's see, this one is, that's the graph of x squared. Now let's graph the square root of x. Square root of x looks like this. And notice that this blue graph, the square root of x, is, well, I don't want to call it the same letter, so I'm going to put g of x equals square root of x, since f is x squared. Notice that these two functions, at least part of it, are symmetric about the line y equals x. That's the line y equals x, the 45-degree line. I didn't make it look perfect there, but if you were to take the blue graph and wrap it over the red line, you would put right on top of this. You've got all this extra stuff here, and what that tells us is that if we were to limit the domain of x squared to be only positive numbers, those two functions that I've graphed are inverses of each other. If I were to change the domain to be 0 to infinity, 0 to infinity, then they would be inverse functions, because then the negative wouldn't even exist. We know that we're only plugging in positive, we know that x and y are both non-negative. So it can't be negative. So we would remove that, and then we would have inverse functions. So if we specify the domain and range correctly, or I should really just say specify this domain, then we'd have inverse functions, x squared and the square root of x.